The sum rule tells us that if I have two functions, u and v, both of which are differentiable, then the derivative of their sum is the sum of their derivatives. That's a very nice rule. This is probably the rule we would just make up if we were allowed to make things up. What we're really saying here is that if I have a function that is the sum of u and v, so u plus v of x, then y prime is the derivatives added together. So these two lines saying the same thing, just this one in the Leibniz notation, this one in our prime notation. Well, let's see if we can use this rule. So let's say I have a polynomial x squared plus x to the fifth. Well, this rule says that I can take that derivative just by taking the derivative of each individual term. And I have a 2x plus a 5x to the fourth, and there's my derivative. I think if I were to do this again, I could skip this middle step and just take the derivative of each one and add them together. So let's do one more. Find y prime. I have another polynomial, y equals 2x cubed plus 3x minus 4. And what I realize now is I can use my sum rule to isolate each term, right? Just take the derivative of the first thing, the second thing, and the third thing, and then add them together. So, the power rule says the derivative of x cubed would be 3x squared. The constant multiple rule says I need to multiply that by 2. So 3 times 2 is 6. Take the exponent down by 1. Plus, the derivative of 3x is 3. I have two different ways of thinking about that. This is a linear function, so its derivative is its slope. I never want to forget that. But I could also use the power rule. 1 times 3 is 3 times x to the 0, and x to the 0 is 1, minus 4. This is technically a sum rule. So what I could do is tell you that's plus a minus 4. And then say, well, that's a constant, and the derivative of a constant is 0. So there's my nice, happy derivative. Now that I know the constant rule, the sum rule, and the constant multiple rule, I realize I can take a derivative of any polynomial very easily, just going term by term. Find a derivative. F of x is equal to 2x to the 50 minus 10x to the fifth minus 4x plus 8,753,940. Just a number I made up. I didn't even say that number correctly, but I'll just lean in. 8,753,940. All right, actually, I might have done that right. Doesn't matter, big number. Let's take a derivative. I'm going to go term by term. 50 times 2 is 100, x to the 49th. 5 times a minus 10 is minus 50, x to the 4th. Minus 4, and then the derivative of a constant is 0. So no matter what ridiculous number I wrote there, I was always just going to say, hey, the derivative of that constant is 0, and there's my nice, happy derivative. G of x is equal to 3x squared minus 4x plus 5 root x. All right, so not a polynomial with that square root of x in there, but I still get to take the derivative just doing the things I've thought about so far. Pause the video and try to take this derivative using the rules we know so far on your own. All right, g prime, 6x minus 4. And now I need to think about that root x as an x to the 1/2. 5 over 2, right? Because 1/2 times 5 is 5 over 2. X, and then 1/2 minus 1 is minus 1/2. So I have 6x minus 4, and I don't like leaving something with a negative exponent, so I'm going to rewrite that as 5 over 2 root x. And there's my nice, happy derivative. Oh, we'll do plenty more examples, but let's learn some more rules first.